Hello everyone, welcome to my presentation. My name is Fengcai Wen. I am a PhD student from Software Institute at Università della Svizzera Italiana. Today, I'm going to talk about my research work on the topic of an empirical study of quick remedy commit. Before digging into the research details, I would like to start with a brief introduction of the research background. Performing code changes is the routine of a developer's daily life. Software systems need to be continuously modified in order to be more powerful, achieve higher quality, and higher stability. As we know, in the version control system, code changes are usually recorded and managed via local commit and will be pushed to remote repository whenever necessary. While working on the project using versioning system, developers usually put several related code changes through different parts of the code into one commit for adding a new feature, fixing a bug, or refactoring the code. However, in some cases, developers may forget or miss some part of the necessary code changes in one commit and unintentionally leave the coding task unfinished. Let's check an example here. From the commit on the left-hand side, the developer implemented a code refactoring to simplify the code of GPAction class. In particular, instead of invoking the method getInstance multiple times in different parts of the class, a variable called language is instantiated and reused wherever needed. However, a few minutes later, the same author performs another commit with a commit message saying, forgot one refactoring of language in previous commit. This second commit propagates the change introduced by the refactoring to another location of the GPAction class, which was missed by mistake in the original commit. In this case, we consider the second commit on the right-hand side as a remedy commit. In addition, if the remedy commit performed within 5 minutes after the original commit, we identify it as a quick remedy commit. Later, I will explain why we use 5 minutes as a threshold here. In our research work, we try to answer the question what type of quick remedy commit are made by developers. Our target was to define a taxonomy of quick remedy commit. Now I will move on to the research details and start with the data collection part. From GitHub, we selected 1,500 Java projects with some predefined constraints to make sure those projects are real projects. And then we mine the complete history of those 1,500 projects and gather the information of the time intervals between all the adjacent commits. We use 5 minutes as a threshold, which is the first quartile of the distribution, to filter out those remedy commits are not quick enough. After this process, we have around 1 million commits left in our dataset. For the next step, we need to define an approach to identify those remedy commits from the 1 million commit. We started with analyzing the commit messages from each commit in this dataset. We listed all the 1 grand words and 2 grand words appearing in those commit messages, and then we sorted the result by frequency. Then we manually inspect those keywords from the list with checking the real example commits which contains those keywords. Finally, we define a lexical pattern, as you can see from the slide. So those commits with the commit message matching this pattern, we will consider they're the candidate commits of quick remedy commit. Finally, we have 1,500 commits left. And then we set up a web application for the labeling. The web application will randomly assign 500 commits to 3 authors. Each commit will be classified by at least 2 authors. If there is a conflict between the 2 authors for labeling the same commit, then that commit will be assigned to a third author to resolve the conflicts. After the labeling process, we built a taxonomy of quick remedy commit, which is the main result of our research work. I will show you all the main categories from this taxonomy on the next slide. We have 6 main categories from the taxonomy, which are bug fix, code refactoring and cleanup, build issue, missing code change, documentation, and reverted commit. As you can see, the number at bottom right corner means the number of remedy commits that belongs to these categories. In this presentation, I will not dig into the detail of all those categories, but I will show you some examples. Let's start with the bug fix categories, which groups these remedy commit fixes a bug introduced in previous commits. Under the bug fix, we have 2 subcategories, fixing of the testing code and fixing of the implementation code. The fix to the implementation code are mostly some classic bugs. For example, fix a wrong return value, fix a wrong if condition, or fix a wrong method reference. Those bug fix cases are interesting since they represent the bugs fixed by the developers within 5 minutes, which might indicate that these bugs are likely quite simple to fix. So here comes an implication. We believe that researchers could learn from this data and investigate the possibility of creating approaches on how to avoid and automatically fix those simple bugs. For example, a recent work applied neural machine translation models to automatically fix bugs. However, given the complexity of the task, they are usually only able to automatically fix a minority of the bugs provided as input. Focusing on these simpler but quite frequent bugs could represent a good application scenario for the neural machine translation-based approach. Besides the fixing of classic bugs, we have another interesting subcategory here, which is the change propagation. We find out that developers sometimes did not propagate a change across all the relevant code consistently, and this is typical of cases in which code clones are spread in the system. There are already some techniques can help developers avoid inconsistent code changes, so the cases we find highlights the relevance for practitioners of those techniques. Also, for the research community, we need to continue improving these techniques, making them easily pluggable into a continuous integration pipeline to foster developers' adoption. Then we move to the second main category, which contains those remedy commits trying to refactor and clean up the code previously introduced. Under this category, the cleanup and code refactoring can be a formatting cleanup, like the fix of indentation style, the ordering of the field declaration. It can be removing the debugging code introduced from the previous commit. It also can be some common refactoring operation like extract method refactoring. Then let's move to the next main category, which is the build issue. Under the build issue category, we have those commits that fix an error in configuration file, and it can also be fixed an issue in build script sometimes. But the main subcategory here is the syntax error. Some cases were violating the syntax due to typos, for example, a missing statement separators. However, we also find many cases of broken references due to the rename refactoring. These refactoring actions are related to variable method classes as well as packages. Considering the good refactoring support provided by modern IDEs, the identification of these commits with broken reference as a consequence of refactoring was quite surprising for us. One of the reasons behind might be this refactoring were performed manually, but still we believe that additional investigation focused on this specific type of errors is needed to understand the reason behind the scenario. The next category is the missing code change. We divided the commit here into two subcategories. The first one is to commit the file miss in previous commit, which is related to a commit error. This issue is mainly caused by an incorrect selection of committed files by the developer, or it can also cause by an IDE cache issue. While this subcategory is kind of unrelated to artifact changes, it still provides hints for interesting research directions. For example, approaches to automatically identify the set of files to commit can be designed to reduce the possibility of missing file and to exclude some unrelated changes. The second subcategory here is to complete previous implementation. One example we find here was the developer claimed he implemented 3 subfeatures in the commit message. However, he forgot to actually implement one of those subfeatures, and he added the missing implementation in the following commit. As a future research direction, this issue can be possibly spotted automatically through techniques that be able to compare what described in the commit message and what has been actually implemented in the code changes. Our next category groups those remedy commits try to fix an issue in software documentation, including release note, license statement, code command, commit messages, and README file. And our last category is the reverted commit. In this case, a developer preferred to quickly bring the code back to its previous state to double-check the implemented change and understand the cause of the introduced issues. Also, we observed in some cases, the code changes were reverted backward and forward within a few subsequent commits, but we couldn't understand the reason behind that. Anyway, we believe that the presence of reverted commit in the history of software system is relevant for the mining software repository research community. For example, considering reverted commit may or may not introduce bias in the study using the history of code changes as a proxy for the developer's experience. So, empirical study aimed at assessing the impact of considering reverted commit on the finding of mining software repository studies may help us to answer the questions. Now I would like to wrap up my presentation with a few conclusions. So in At our research work, we firstly define those commits, quickly fix an issue introduced from the previous commit as a quick remedy commit. And then we built a taxonomy of quick remedy commit by manually analyzing 500 candidate commits selected. For each category in the taxonomy, we describe a concrete representative example and provide implication for both practitioners and researchers. And as a future research work, we plan to enlarge the set of manually analyzed commits to test the generalizability and completeness of the defined taxonomy. We will also work on some of the following research directions which we have learned from the implication discussed before. For example, like automatically fixing simple bugs, automatic identification of omitted changes, or study on the impact of reverted commit on MSR studies. Thank you for watching my video. I'm looking forward having a discussion with you if you're interested in our research work. Bye bye.